After defining the strategies and utilities in the Bayesian game, the next obvious thing is to define the equilibrium concepts in Bayesian games. So now we know that in Bayesian games you have two different stages in which you can observe your types. So the first stage is where you do not observe your type, yet you can make certain decisions. And in the second stage, after you have observed your type, you may have some belief about the types of the other players. So accordingly, we can also define two equilibrium concepts. And the first equilibrium concept is the vanilla Nash equilibrium concept, which talks about the same utilities. So we have already discussed what is this ui sigma I star sigma minus I star mean. So that is the definition of utilities, ex ante utility. And if that is at least as much as the ex ante utility when agent I is changing its type to sigma I prime, if this inequality holds for every sigma I prime and for every player, we call that this sigma I star is a Nash equilibrium with respect to this common prior in this Bayesian game. So here we have one additional feature because these games are not deterministic games. On the other hand, when we talk about the ex interim thing where the players have observed their own type, then the equilibrium concept that we will be discussing is called the Bayesian equilibrium. The only thing that changes is the utility. Instead of utility being an ex ante utility, it becomes an ex interim utility. So we know that this is the utility expression for player I when player I is choosing sigma I star, and other players are also choosing sigma minus I star. The utility here has to be at least as much as the utility when agent I is moving to sigma I prime. So unilateral deviation only in the for player I, and that is not going to give him any better utility. Now, one simple exercise, it is very similar to what we have done in the context of mixed strategy Nash equilibrium. You can equivalently replace this definition with something like let's say AI prime. So you can look at any action and if you can satisfy this inequality for any AI which is living in capital AI, then also it is the same, it's an equivalent definition of Bayesian equilibrium. The idea, so the forward direction should show that whenever you have this definition of Bayesian equilibrium, you can always go to that is obvious. But the reverse direction requires a little bit of work, but that is very similar to what we have done in the context of MSNE. I'm not going to do that exercise once more. Leave it as a homework. Now, the thing that we should notice is that the Nash equilibrium concept in this case, the first one, is taking an expectation with respect to p theta. So even for player I, it is taking the expectation with respect to its own type because it has not observed its type yet. While for the Bayesian equilibrium, it takes the expectation with respect to the conditional probability. It observes its own type, and then it takes the conditional probability over this theta minus I, given theta I, and then takes this expectation. Now, even though it should give some more information, and the notion of Bayesian equilibrium must be something stronger than the Nash equilibrium, the following theorem says that in finite Bayesian games, a strategy profile is a Bayesian equilibrium if and only if it's a Nash equilibrium. So note that this sigma i's are still mappings from this set capital theta I to the simplex of AI. So it is, even though they are being treated differently, Bayesian equilibrium and the Nash equilibrium, the sigma i's are essentially living in the same space. So it is meaningful to talk about their equivalence, and this theorem says that they are identical whenever you have a finite Bayesian game. So how should we prove this? So let's look at the forward direction. That is, we are given that this sigma star comma p is a Bayesian equilibrium. Then we'll have to show that this is also a Nash equilibrium. So let us start with the strategy for player I, which is sigma I prime. So player I is actually deviating to sigma I prime. Now I know that you can write this as the expectation with respect to theta I, and the inner utility is the interim utility for player I. Now I know because this theta star is a Bayesian equilibrium, this quantity should be less than or equal to this quantity, right? And therefore this inequality should hold. This b theta i's are all non-negative quantities, actually all positive quantities. So this inequality will not get flipped. So this, when you look at this expression here, this is nothing but the utility of player I when it is also picking sigma I star. So this is what we wanted to show. This is the definition of Nash equilibrium. So we have shown that if it is a Bayesian equilibrium, sigma star comma p, it is also a Nash equilibrium. The other direction we will prove it via contradiction. That is, we'll have to prove that if it is a Nash equilibrium, it has to be a Bayesian equilibrium. Rather, we will say that if it is not a Bayesian equilibrium, then we will show that it cannot be a Nash equilibrium either. So which will be then prove the contradictory statement. So let's start with this. So suppose this is not a Bayesian equilibrium, and now we are going to use that the second formulation of the Bayesian equilibrium. So we have just said that when you look at the second formulation of this Bayesian equilibrium, you can replace this with a prime, and this should hold for all ai primes that is living in capital AI. Now the negation of this statement will be there exists some ai prime or ai for which this inequality is flipped, and for some player and for some type. Right, so there exists some player I in N, some type theta I, and some action AI, such that this inequality holds. And now the job is to construct a specific sigma I hat, such that you can show that it is actually doing better than the claimed Nash equilibrium. So the sigma I star, if we can show that it for player I at least it improves the expected utility, then we can say that this is not going to be a Nash equilibrium for player I either. So how do we construct that? So for all the types that are living that is not equal to theta I, so for all the types that are not theta I, we just keep it the same as the sigma I star. Only for theta I, we do the following: we put all the mass on this action AI. This is what you would have expected. We have a place where we can strictly get better off, then we should put all the mass on that action, and for all other actions we put no mass. Now you can write that down, the expectation expansion of this utility expression. So you have this E of theta I hat. So just to denote that this is a running variable, we have used a different notation. So the inner sum is the x interim utility for player I. Now you can break it up into two pieces. One are the all the types of player I which is not equal to theta of I, and the other term is for theta I. But at that point we already know, so this is just singling out one particular term from this sum. We know that this particular utility is going to be strictly greater than theta I star. For all the other things, so for all the other stuff, it is going to be exactly equal to. So this terms we already know that these are equal to theta I star of sigma I tilde. This is by definition the way we have constructed this sigma I hats. But for this one, it is going to be strictly better, and therefore this inequality will also hold. This sum will be at least as much as so this will be strictly more than this utility, and we know that this can be replaced with sigma I star theta I tilde. So therefore, what you get on the right hand side is the utility at sigma I star sigma minus I star. So therefore, this sigma. So we have actually found one mixed strategy for player I which strictly improves the utility of player I. over sigma I star sigma minus I star. So therefore this cannot be a Nash equilibrium either. So hence this is proved. We started with something that is not a Bayesian equilibrium. We showed that that is not a Nash equilibrium. So therefore the other direction is also proved. Now the very important question of existence, we know that Nash equilibrium exists. What about Bayesian equilibrium? And the answer is very simple. For finite Bayesian games, where we mean by finite as the set of players, the set of actions, and the type sets all are finite, then this game must have a Bayesian equilibrium. So again, we will not get into the proof. You can look at the addendum, which will be posted to look at the complete proof. It is actually a little messy. You'll have to write it down appropriately. But the idea of the proof is that you will have to transform this Bayesian game into a complete information game. How can we do that? By treating each of these types of this type sets as a different player. You can consider, so let's say we have theta 1, which has, let's say, 3 elements, theta 1 1, theta 1 2, and theta 1 3. We can create a larger set, and maybe similarly there is a capital theta 2 which also has similar terms. Now we can actually create a larger set of players where each of these types are actually one player, and you can define the utilities appropriately. Whatever we were defining as utility at a particular type of a player and a particular action, we can now imagine that that type itself is a player, and therefore the action is the action that has been chosen by that player. And therefore we are in a complete information setting now. We have blown up the space of the players, but now since everything is finite, that will also be a finite set. And in the finite complete information game, we know that by Nash theorem that the equilibrium, the mixed strategy equilibrium, must definitely exist. And we can also show that that mixed strategy in that transformed game is also a Bayesian equilibrium in the original game.